Welcome to today's Explainer. We're jumping right into it because today we're exploring the invisible heartbeats of our modern world, synchronous machines. We are looking at two absolute titans of electrical engineering that literally power and move everything around us. Have you ever wondered how the water rushing through a dam miles away ends up powering the very screen you're looking at right now? Well, you are definitely in the right place.
What's immediately striking about these machines is their perfect symmetry. It's a complete duality. On one hand, we have the synchronous motor, taking electrical energy and transforming it into physical, mechanical motion. And on the exact opposite side, we have its mirror image, the three-phase generator. This one takes mechanical motion and turns it right back into electrical energy. They do the exact opposite jobs in our power grid, yet, as we're going to see, they're intimately connected.
Here's our roadmap for today. We'll start with the basics of electrical machines, then get into the synchronous motor working method, followed by what is a three-phase generator. After that, we'll hit the important part, the armature, dive into synchronous speed and calculation, and wrap it all up with the relationship between motor and generator. Let's get to it.
Section 1. Basics of electrical machines.
Before we get into specific applications, we really need to understand the foundational pieces they both share. First up is the stator. Just like it sounds, this is the stationary part of the machine. It's this immovable, heavy outer shell. The core of this shell is laminated, which means engineers use this incredibly clever trick of layering thin sheets of magnetic material. Why? To minimize something called eddy current loss. Basically, it stops the machine from wasting precious energy as useless heat. Tucked inside this highly efficient shell is the three-phase winding.
Now, in total contrast to that stationary outer shell, we have the rotor. This is the dynamic, spinning heart of the machine, tucked right inside and connected directly to the main shaft. The rotor carries magnetic poles, and it gets those poles either by being fed direct current, which we call DC excitation, or from powerful permanent magnets. It's the magnetic interaction between that stationary stator and this rapidly spinning rotor that makes the whole thing work.
Section 2, Synchronous Motor Working Method. You'll find these heavy-duty synchronous motors in constant speed applications. Things like massive industrial compressors, large-scale blowers, and heavy factory conveyors. Think of how they operate kind of like a high-speed chase. We feed a three-phase AC power supply into the stationary stator. Because of the alternating nature of that supply, it creates a fast-spinning, invisible tornado of magnetism inside the machine, literally a rotating magnetic field. So our rotor, which has its own magnetic poles, feels this spinning field and starts chasing it. It's desperately trying to align its north and south poles with the stator's shifting field until, bam, they lock together at the exact same speed. That perfect, unwavering lock is what we call synchronism. There's no slipping behind, they move as one.
But, and this is a really fascinating quirk of physics, it is absolutely not self-starting. See, because the stator's magnetic field is instantly spinning at full speed the exact second you turn on the power, the heavy stationary rotor is essentially left in the dust. It just sits there vibrating in place, totally unable to catch up to this blur of magnetism. So, to solve this, the rotor needs a little push to get going. Engineers use some brilliant workarounds like a damper winding, a smaller helper motor called a pony motor, or a variable frequency drive. These gently ramp up the speed so the rotor can safely catch the field and lock in.
Moving right along to Section 3, what is a three-phase generator?
Okay, I want you to take everything we just learned and flip it entirely in your head. We are now looking at the machine responsible for creating the vast electrical grid that powers our homes and cities. Instead of plugging the machine into the wall to get motion, we use physical force, like high-pressure steam or water rushing through a massive hydroelectric dam, to physically spin the rotor. This external driving force is called the prime mover. So as this magnetized rotor forcefully spins, its magnetic field sweeps across the stationary wires of the stator, literally cutting right through them. Thanks to Faraday's law of electromagnetic induction, this slicing action forces electrons to move, inducing an electromotive force, or EMF. Just like that, we've turned rushing water into electricity.
And the absolutely crucial factor here is this 120-degree spacing. Because the stationary windings in the stator are physically spaced out, the spinning rotor generates 3 separate waves of electricity spaced perfectly, exactly 120 electrical degrees apart. This right here is the absolute magic behind three-phase power. It is exactly why major power lines usually come in bundles of 3. It delivers a smooth, incredibly efficient, and continuous flow of energy that a standard single-phase system just cannot compete with.
Section 4. The important part, the armature.
The armature is a term that gets thrown around a lot in electrical engineering, but its definition is actually very precise. It is the winding where the actual transfer of electrical power occurs. It's the exact location where that induced EMF is generated. It is where the real action happens, basically. Now, what's really fascinating is that in both of the synchronous machines we're discussing today, whether it's the motor converting energy or the generator producing it, the armature is almost always placed on the stator winding.
So why do engineers smartly place this heavy-lifting armature on the stationary outside rather than the spinning inside? Well, it's pretty brilliant at its practicality. First off, it makes it incredibly easy to extract a high-voltage output directly from stationary cables. You definitely do not want massive amounts of high voltage on a rapidly spinning rotor. I mean, that is a safety and engineering nightmare. By having it safely stationary on the stator, things like insulation, cooling systems, and general maintenance become vastly easier and much more reliable.
Section 5. Synchronous speed and calculation. The math linking these machines dictates the design of power plants globally, and it all centers on one golden rule. NS equals 120 times F divided by P. Let's break that down. NS is the synchronous speed, meaning how fast the machine must spin to stay in perfect harmony with the electrical grid. The F stands for the frequency of your power supply, which is typically 50 or 60 Hz, depending on where in the world you're watching this. And finally, the P stands for the number of magnetic poles actually built into the rotor.
Let's see how this actually plays out in real life on a standard 50 Hz grid. If you build a machine with just 2 poles, it has to spin extremely fast, 3,000 revolutions per minute, just to stay in sync. But if you design it with 4 poles, that required speed drops by half, down to 1,500 RPM. Add even more poles, say 6, and it slows down to just 1,000 RPM. This incredibly direct relationship dictates exactly how engineers design alternators. For instance, a fast-spinning steam turbine might only need a 2-pole generator, while a slow, massive water turbine at a dam needs a generator packed with tons of poles to hit that exact same 50 Hz target.
Section 6. Relationship between motor and generator. Let's bring everything we just learned together and revisit this core duality. Think of a motor taking an electrical supply, creating a rotating magnetic field, and physically forcing the rotor to follow it, which creates motion. Then, think of the generator using a prime mover to physically spin the rotor, which cuts through the stator and induces the electrical supply. They are truly 2 sides of the exact same electromagnetic coin. In fact, theoretically, you could take a synchronous generator, plug it into the wall, and run it as a synchronous motor. It's the exact same machine playing 2 different roles. And this just brilliantly illustrates the elegance of electrical engineering. Whether you are powering a massive industrial compressor on a factory floor or generating that exact power miles away at a towering hydroelectric dam, the foundational physics remain identical. Both rely on the intricate dance between the stator and rotor, both depend on magnetic field interaction and strict synchronous speed, and both are universally governed by Faraday's law of induction. It's the exact same rulebook.
Which leaves us with this final question. How many synchronous machines powered the device you are watching this on right now? Seriously, think about it. The electricity charging your batteries started at a massive 3-phase synchronous generator. It was likely pumped, regulated, and processed by synchronous motors all along the industrial grid before finally reaching your home. You are connected to an invisible, perfectly synchronized chain of spinning magnets that make our modern life entirely possible. Thank you so much for joining me for this explainer. I really hope you found it as fascinating as I do. Catch you next time.